Hello guys, so in this video we are going to prove GCD equation. So the GCD of two numbers A and B is given by the equation AX plus BY, where X and Y belongs to the set of integer. Alright, so before we go ahead and prove this, let us understand two concepts. So let's see concept one. Well, this is not a concept but more of a notation. In maths, we write A divides B. Basically, what it simply means is, let's say 2 divides 4, right? Here, 2, 4 is divisible by 2, which means the remainder is 0. So that is why we say 2 divides 4, right? Similarly, one more example could be 3 divides 6 or 6 divides 18, right? So this is how, if a number divides another number, then we'll say A divides B and we represent it as something like this. Similarly, if A is not able to divide B, then we will write it as A does not divide B. So that is notation 1. Now let us look at the concept 2, and this is something, well, we all of us will probably be knowing of it, but let me just put it down over here so that we since this is something which we'll be using it, so it's better to brush these things up. Okay, so let's see the concept 2. Well, concept 2 basically formalizes our division. So what do I mean by this is, basically, let us say like 28 is a number and I want to divide it by 3. Okay, so 3 8 times 24 and then 4. So 8 is our quotient, 4 is our remainder, 3 is our uh, divisor, and 28 is our dividend. Or I'm sorry, I might be confused between dividend and divisor. But anyway, you get the gist. So essentially 28, how can we write 28? 28 is basically 3 times quotient, right? Sorry, yeah, 3 times quotient plus remainder, right? So let's say A, and if we have to write in terms of A and B, and let's say we say A does not divides B, then we can say that B is equals to A times some quotient Q plus R, right? So in the case where A was 3 and B was 28, our Q was what? Q was 8 and remainder was 4, right? So this is how we can formalize the division. Okay, so this equation is something which we have to note, and depending upon this equation there are some properties of remainder, and that is what is we want to understand. Properties or constraint, you can say. Properties or constraint, let me write it down. Constraint on R. So what we want to find out is, what is the minimum value? Is the minimum value of R. R is, please note, R is remainder, and similarly, what is the maximum value of R? So the minimum and maximum is something which we want to find out of R. Okay, so let us take the minimum value. Well, the first question which we need to ask ourselves is, can R be a negative number? So if you are dividing two numbers and let's say the two numbers are positive, can R be a minimum number? Can R be, okay, let me just rewrite it down. Can R be less than 0? Is it possible? Well, clearly this is not possible. this is not possible, right? So that's the first one. The second one is basically if A divides B, then what will be the value of R? R will be 0, isn't it? So for instance, 2 divides 4. And if you want to divide 4 by 2, the remainder will be 0, right? So that is why the minimum value R could attain is 0. Since it could not be negative, so the minimum value which R could attain is 0, right? So R should be greater than or equals to 0. And R should be what? R should be less than something. So let us see what is the maximum. So this is what the minimum, when we pose the question, what is the minimum value of R? This is the answer for it. The minimum value for R is 0. And now let us try to answer the maximum value of R. Now if you are dividing any number, let's say I am trying to divide 7. I'm trying to divide, let me just say 47 by 7. So the max it could go is 7, 6, 42. Remainder is 5. So the remainder is 5. Now the question which we need to ask ourselves is that is it possible for R to be equal to 7 if our dividend and divisors, if our dividend is 7? Is it possible for us to have R greater than 7? That is not possible, because anytime you divide a number, the remainder has to be less than the number with which you are dividing it. So remainder has to be less than A in this case. Okay. So let me just rewrite it one more time. So in the, okay, just a second, this is a bit difficult. Okay, so in the case where A does not divide B, then B can be written in the form of AQ plus R, where R is less than or equals to, greater than or equals to 0, and less than, it has to be less than how much? A, right? So this is something, this is something which we have to be aware of in order to understand the proof of GCD. Alright, so let us begin the proof. So we want to prove GCD of A comma B is AX plus BY, right? So, and where X and Y belongs to the set of integer. Okay, so first let us try to understand what do we mean when we say GCD of A comma B is AX plus BY. Well, what we actually mean is that, well, to explain it better, let me say that there is an set R which consists of element R such that R is equals to AX plus BY and R is greater than 0 for all X and Y belonging to the set of integer. So for all X and Y belonging to set of integer and R greater than 0, R is the element of capital R. So then, the R will contains elements like R1, R2, R3 and so on. Okay. Now let L be the minimum of R. Okay. Let me just scroll a little bit up. God, this is, so if L is the minimum, okay, so if L equals to minimum of R, and this is what, then L equals to AX plus BY, because all the elements of R is coming from AX plus BY notion. So that is why L equals to AX plus BY, and this is what is the GCD. And this is what we mean when we write that GCD of A comma B equals to AX plus BY, we simply mean that there is a set R which consists of positive elements. So let me see. So there is an set R which consists of positive elements. Okay. Remember, please note this R greater than 0, which consists of positive elements, and of this set, the minimum positive element is something is what the GCD of A comma B is. Alright, so that is what we mean by GCD of A comma B when we write GCD of A comma B equals to AX plus BY. Okay, I hope the meaning of GCD is clear. GCD, when essentially when we write GCD equals to AX plus BY. Okay, now let us prove it. So let L be the minimum. Let L be the minimum of R. So L equals to AX plus BY, right? Since, and why is it so? Since L belongs to R, right? And all the elements of R are of the form AX plus BY. That is why L equals to AX plus BY. All right. Now let us see whether L can divide A and L can divide B. All right. Now it is possible that L will actually L divides A. If L equals to AX plus BY, then L divides A and L divides B. This is one lemma which we will prove also, but this is something which will happen. Okay. So let us prove this. Let us prove that L divides A, and similarly we can say L divides B. So let us try to prove this. So we will just prove L divides A, and by the similarly we can also prove that L divides B. Alright, so now we know that L equals to AX plus BY. Okay. Now in order to prove that L divides A, we'll prove it by contradiction. So we will say, if possible, let us assume that L does not divide A. Okay, if it is possible. Now since L does not divide A, so remember from our discussion before we starting the proof, if A does not divides B, then B equals to AQ plus R, where R is greater than equals to 0 and R is less than A. So by applying the same, what we can write down here is, since L does not divides A, so which means A equals to L times Q, some quotient, and R. And what is the constant on R? R should be greater than equals to 0 and R should be less than, okay, R should be less than L. Please note that in this particular case, R is not, it cannot be equals to 0 because A does not divide L. So there should be some remainder, which there should be some non-zero remainder, and that is why R cannot be equals to 0. But anyway, R greater than equals to 0 is also fine. Okay, so now A equals to LQ plus R. Now let us plug the value of L in this equation. So what was L? AX plus BY, right? Plus R. Now let us represent L in the form of A's and B. So L is basically equals to, R is basically equals to 1 minus QA, right? Plus, we can write down minus BQ times, or okay, let me just write it down. Sorry about this. Plus minus BY times, oh, I am so sorry, minus sorry, BQ times Y, right? Okay, okay. So this is something again in the form of AX plus BY, right? Here, here X is equals to 1 minus QA and Y is equals to what? Minus B times Y. Okay. So again, so now since, right, so here R is also, R is in the form of AX plus BY and R is greater than 0, right? Greater than 0, right? R cannot be equals to 0. Please understand that because of our assumption that L does not divides A, right? Since it does not divide A, since L does not divide A, then there has to be some non-zero remainder, and because of that 0, since it is a non-zero remainder, so because of that reason R has to be greater than 0. Now since R can be written in the form of AX plus BY and R is greater than 0, so we can safely say that R belongs to the capital set, the bigger set R, capital R. Okay, I hope that makes sense. Okay, now what do we now let us try to see what is the relationship between relation rel- I'm sorry about this, relationship between L and uh, L and R, right? L belongs to R and R also belongs to R, and L is the minimum, right? Is And let me just write it down like this. L is equals to minimum of R, and from our equation, let me just scroll up a bit to show you that equation. When we write it down, when we said A equals to LQ plus R, we said that R is less than L, right? So from the same equation, we can write it down that R is less than L, right? And R, and if you compare these two, if you look at these two, right? R belongs to R and R is less than L, but L is the minimum. Okay, right? Let me repeat it one more time. L is the minimum. So L is the minimum element which is there in the set R. But here we are coming to a conclusion that there exists an element R which is less than L and belongs to R, right? Let me repeat it one more time. We are coming to a conclusion that there exists an element R which belongs to the set R which is less than L. So this simply means R is equals to minimum of R, isn't it? Right? But we know that L is the minimum of R. So this deduction that R is less than L is wrong, right? And hence we reach to a contradiction. R is less than L is not possible. Not possible. Hence, our assumption that L does not divides A is, I'm sorry, am I dealing with A or B? Okay, does not divides A is wrong. Hence, hence L divides A. With similar proof, we can also argue that L divides B. Okay. So far, what we have understood is basically L equals to AX plus BY, and L divides A and L divides B. So far what we have understood is L, let me take this, let me take a different color. L equals to ax plus by and L divides a and b. This we have proved it. If you feel that the explanation was not proper, please drop a comment. I'll try to answer those confusion. I know this is a bit hazy, but please go through the video and rewatch it. Maybe that will help you. If still that is not clear, please drop a comment. I'll try to explain it as better as I could. Okay, so far what we have understood is that L equals to ax plus by and L divides a and L divides b. All right. So now let's proceed forward. Okay, let me go down. Okay. By the way, I'll be uploading this note also, so that you could refer it. Okay, so far let me just write it down here because I have to go up every time. Okay, so let me do this. L is equals to ax plus by and L divides a and L divides b. So far this is something which we have gone through. Now let us assume G be the GCD of A and B. Okay, since G is GCD of A and B, hence we can write A equals to G times G1 and B equals to G times G2. Since G is the GCD, so it's a common divisor, right? And since it is a common divisor, then we can write it in the form of multiple. Okay, let me just take an example. For instance, okay, let me just scroll a little bit up. Okay, so for instance, if we write let me take 24 for instance, right? And let me see 2. So we know that the GCD of 2 and 24 is 2, right? Now since 2 is the GCD, then 24 can be written as 2 into 12, isn't it? And similarly 2 can be written as 2 into 1, right? So here this 2 and this 2 is the GCD. So by similar logic, I'm writing down this. Okay, so A equals to G times G1 and B equals to G times G2. Let us plug these values in the equation AX plus BY. So L was AX plus BY and L equals to, now what it becomes is X times A is what? G times G1 plus Y times G times G2, isn't it? So from here what we can say is that L is equals to G, if we take in common, X G1 plus Y G2, right? Okay, so from here we come to a conclusion that G divides L. Now since G divides L, this implies G should be less than or equals to L. Okay, and G comma L are greater than 0. Okay, these are positive integers we are dealing with, so that is why G and L should be greater than 0. Now let us investigate, or let us explore this equation bit further. So the question which we should ask ourselves is, can G be less than L? Okay, so basically G is less than L. Is this possible? Well, the answer is no. Why is it so? Answer is no. Why is it so? So let us say G is less than L. Then again G can be written in the form of AX plus BY, And the proof which we did, uh, where so the proof I'm talking about is this, is basically here, which is this. So we did all this proof, a equals to L cube plus R, and then we replace it, and then we come to a conclusion that R is less than L. The similar kind of thing is happening over here as well, where G becomes less than L. Now, since if G becomes less than L, and L is the minimum element of the set R, so G less than L is not possible. G less than L, G cannot be less than L. So what does it leaves with? Leaves us with G becomes equals to L, because remember G was less than or equals to L. Now we know G is not less than L, hence G has to be equals to L, and that is how we prove that G equals to L equals to AX plus BY, and this G is basically GCD of A comma B. Okay, I hope the proof was clear to you. In case if you have any confusion, please feel free to drop it in a comment, and I will definitely visit it again and try to answer your queries. Thank you.